everyone, welcome to lesson 5, collecting like terms. We're going to be talking about algebra tiles a bit today for part of our lesson. So if you haven't used algebra tiles, it's okay. If you have, I'm hoping that this will just help reinforce some concepts from elementary school. First of all, we're going to be using the term polynomial expression. Polynomial expression is an algebraic expression, algebraic meaning letters as well as numbers. And it's made up of one or more terms separated by addition or subtraction. That's the big thing about polynomials. Remember, a binomial would have like 5x plus 2y. That makes it a polynomial when there's multi-terms in it. So what's a more compact way to write 7 plus 7 plus 7 plus 7 plus 7? Well, how many 7s have we got there? There's 5 of them. So 5 times 7 is a better way to write it. And it's a more compact way to write out that kind of calculation. So let's transfer that knowledge to algebra. What's a better way to write m plus n plus n? So we've got 5 m's there. So think of what we just did when we had 5 7s. Now what would we do if we had 5 m's? We would write 5 times m, or we just put it together as 5m. As opposed to up here, 5 times 7, we can actually multiply those together, those two numbers. We can't really multiply a 5 and an m, we just kind of squeeze them together and we make 5m. So if m stands for something like marshmallow, you've got marshmallow, 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 you got 5 of them, well then you've got 5 m's. That's what m stands for. What if it was an m squared? What if we've got an m squared, an m squared, an m squared? So m squared is something completely different from m. If m was marshmallow, then m squared is mountain or something. It's very different. So what do we get this time? We get 5m squared because there's 5 of them. If I had construction paper and I could cut out m squareds with it and I put them on your desk, you would have 5 m squareds with you. They wouldn't be m's. And they wouldn't be m to the power of something else because I cut out an m squared, shape. So next what we're going to do is look at some algebra tiles and see if that helps us make sense of what we're talking about today, which is collecting like terms, which is a real cornerstone piece of algebra. So this means 1. This little small cube is a 1. The same thing in red is a -1. So it's the same size and same shape, but it's a -1. So these shapes are all common algebra tiles. This one is just a 1. This one we call x, and this one is x long and x wide, so this one is called x squared. So we've got x and x squared here. So let's compare the positive and negative tiles. That's a 1. So a -1 is the same thing but red. So if this is x, then what do you think a -x would look like? It would look just like that. And if we have a large square, remember what that is? That is x squared. So the red version of that would just be -x squared. Now let's talk about 0. If I have a +1 and a -1, they cancel each other out and they turn into 0. And 0 pairs are important when we talk about algebra tiles. So same thing with the x's. If I have equivalent numbers of matching shapes, they will cancel out. A positive and a negative will give you 0. Same thing with the x squared. If we've got one of each, then it's really just 0 that you have there. And that's a really important concept for collecting like terms. So we're going to illustrate 3. 3 looks like that. Okay, those are not x's, those are constants. Those are just 3's or integers or just numbers. So -2, what would -2 be? It would be 2 of the red ones. Now, a different way of talking about each of those, I could add 0 on. If I put another positive and another, that's 0, right? They cancel each other out. So this is still 3. It's 4 minus 1. It's still 3 because all I've done is add in a 0. Same with the 2. I've got -2. If I add 1 but then subtract 1, I'm still at -2 because I've only added on 0, and now I've added on another 0 pair. So that's still adding 0 each time. All right, let's look at the next slide here. Representations of terms. Illustrate each of the following terms. So there's 3x's, no problem, right? What about negative 2x squared? That would be the red one, but there would be 2 of them. Now collecting like terms. Let's put all this information together. First of all, 4x. Can you think of what 4x would look like? Hopefully you were thinking of that. And what about negative 2x? What does negative 2x look like? 2 red ones, 2 of the red long ones, rectangular ones. Next, can you picture what 3x squared would be? Hopefully you had that in mind. And what about negative 5x squared? Right? Now, my whole point of today's lesson is the title of this one slide here, collecting like terms. So notice that the x tiles and the x squared tiles do not match. They're not the same. This shape here and this shape here are not the same. I can't add these two pieces together. They cannot be added together. Even if I took a red one with it, it doesn't matter what the color, it's the shape I'm looking at here. These shapes are not the same. They can't be added. These shapes are the same. So the first thing I want you to do is mentally collect all of the x tiles. So these are x tiles. The rectangles are x tiles. So mentally collect all of these. How many will there be once you cancel out the 0 pairs? So remember what 0 pairs are. The 0 pairs mean you can match up a positive one with a negative one. So when we cancel these out, these make 0. What are we left with? We're left with 2x. There's only 2 x's left here. This is our answer. So 4x minus 2x would equal 2x. Now let's look at the squareds. Mentally collect all the x squared tiles, so the yellowish ones and the red ones. Now when you cancel out the 0 pairs, how many have you got left? So do you have an answer in your head here? You don't need to be writing any of this down on your sheet. You probably don't have any room to write any of it down. We're just kind of recapping maybe what you've done in elementary school with the tiles. So I'm just giving you a visual. So how many cancel the 0 pairs? So for each positive that we have, do we have a negative? Yes. And continue on. What have you got left? You got negative 2x left because 3x, these 3 x's, put it here, 3x squared, subtract 5x squared. So I take out the 0 pairs, I'm left with the red. That means there's going to be negative 2x squareds left there. So collecting like terms, if you look at the very bottom equation I've put in there, we had 4x here, and we had a minus 2x there, and we had a positive 3x squared, and then we had negative 5x squareds. All together, we collected all the like terms, and we were left with 2x's and negative 2x squareds, or subtract 2x squared, or minus 2x squared. So this is what we were left with. We collected the like terms, and what's really important to understand is what's like and what's unlike here. So this is going to go through on its own. This is going to just put up a bunch of polynomials. Remember, polynomials have this is a trinomial because there's 3 terms and there's a subtraction or addition sign. This is a binomial because there's 2 terms. But over here, when we look at them with the tiles, we just have a visual representation of what x squared is, minus 3x's and plus 2. So this is just a visual representation for you of what the polynomials are. And again, a polynomial expression is an algebraic expression made up of 1 or more terms. So this is binomial, binomial, trinomial, separated by addition or subtraction. So these are all polynomials. When you get to do your homework, there will be questions that tell you use algebra tiles. You may not want to because maybe you didn't use them in elementary school and you're not comfortable with them, and if you're at home right now, you probably don't have algebra tiles at home. You could draw them if you wanted to, but you don't have to use algebra tiles. But I want to make sure that you've had some understanding of them anyway. Let's just try model. We want a positive 3 and we want to add on a positive 2. And these are just integers. These are the little square ones. So there's 3. There's 2 more. When we add them up, of course, we have 5. That's pretty straightforward. So what if we change that to x's? What if I want positive 3x tiles and I want positive 2x tiles? So there's my 3x tiles. Now I want 2 more. I can add those together because they're exactly the same. Those are like terms, and that's the point of today's lesson, right? Those are like terms. So what have I got? 3x plus 2x equals 5x. This is, you only need to really do this in your homework if you want to. If you had a question like this using algebra tiles, you don't need to draw them out. You can just go ahead to this step if you're ready for it. If you don't think you need the tiles, then you can go ahead and move right to just writing out your answer like that. Let's try another one. With the tiles, 3x plus 1 plus 2x minus 3. So can you, in your head, get an idea of what that will be? 3x, you know what that is, and then a single 1, 2 more x's, and a negative 3. So that's going to change the color. So there's 3 x's. There's that single 1. We need 2 more x's, and now we're going to subtract 3. Those are the red single squares. So when we collect all of that, what have we got? What's the answer? Can you come up with an answer? Let's start with the x's. How many x's have we got? And then go to the integers. Cancel out your 0 pairs. How many integers have we got? Hopefully you came up with 5x minus 2. Okay, now we're back to your handout here. This is the last slide. Without the algebra tiles, what is m plus n plus n plus w plus w? So they don't have to be x's, they can be any letter. But what's important is that you recognize that the m's and the w's are different. If the m stands for marshmallow and the w stands for wheat, we can't put those two things together. We've got 3 m's here, and we've got 2 w's there. We don't have 5 of something different, mw or something, right? We are adding, they have to be like terms to add them. So all we have is 3m plus 2w. We can't go any further and collect those two. They're not like terms. They're not the same shape. If we had a tile for them, the m might be, I don't know, an octagon, and the w would be maybe a circle. But we can't put them all together and get 5 of a brand new shape that we're going to invent here. The main rule for today's lesson is you can only add or subtract like terms. So let's just clarify. What are like terms? Definition. Like terms have matching variables, that's the letter, bases, and exponents. So this is an m. If it were an m squared, it could only match up with another m squared. The number in front, that's the coefficient, doesn't need to match for it to be a like term. So it doesn't matter that this is a 3 or a 2. The reason they're not like terms is because one's an m and one's a w. The number in front doesn't matter. Let's try some examples here. So if the first, I'm giving you 7a. That's your first term. It's a 7a. So again, we don't need to worry about the 7. That doesn't tell me if it's a like term or not. Like term is just the variable, in this case an a, and the exponent. I don't have an exponent. I have an invisible 1 there. So what's like term with 7a? Again, imagine I am physically cutting out a letter a and giving it to you. So you've got 7 of them, 7 letter a's in front of you. Some like terms with that are all of these. 2a. Right? If you have 7 a's in front of you and I give you 2 more a's, can you add them together? Yeah, you can, and you get 9 a's. That's fine. You can add or subtract. Those are like terms. A negative a, for sure. It's just a different color, like the algebra tiles. 7a, you've got 7 a's in front of you. I take away an a, now you've got 6 a's. 0.75a, sure, it's a decimal. It makes things a little harder, but we can add and subtract numbers that are fractions or decimals, or positives or negatives. These are all like terms because the letter is an a and the exponent is an invisible 1, so it matches. These are all like terms. Equally as important is for me to talk about what unlike terms are, because that's what most commonly where we make our mistakes. We confuse what's unlike and what's alike. So these are all unlike terms. 7ab is not the same as 7a. Again, if you have 7 A's in front of you, literally you have the letter A, but you have 7 of them in front of you, and then I give you an A times a B pushed together like that, they're not the same. And this is an A squared. We know that from our algebra tiles. A square is this is a squared shape. This is not. These are not the same. And I'm specifically using 7 over and over again here, just so you don't think if the number in front is different. If the number in front is the same, it doesn't matter. This is a constant, that's just 7. 7 over a is not the same either, because that's a denominator of a, and you know from your exponent rules that when you have something left on the bottom, it's not the same as it being on the top. And negative 4a cubed, well, that's not the same either. It's completely different exponents. So those are unlike. So don't get tricked into thinking, well, look at this 7ab, it looks a lot like this one. I think I can add them. You can't. They have to have a matching variable, and the exponent has to be matching exactly. Let's try again with 2x squared. What are some examples that are like 2x squared? All these I could add to negative 2x squared. If I have negative 2x squared, that would be the red large square tiles from before. If I had 2 of those, this is a 1x squared. This is a single 1, and I could add that on. When you don't have a coefficient in front, it's an invisible 1. If I gave you 13 of those tiles, but I would be giving you the orange color because this is positive, could you put them together with these? Yeah, you could collect them all, get some 0 pairs, and you'd end up with 11x squared. 3/4 x squared, that's harder to visualize with tiles because we don't cut up the algebra tiles into 3/4. But certainly we can take a negative 2 and 3/4 and we can add and subtract these two even though they're fractions. This one is good too. As long as the x squared is in the numerator, it's the same as putting it to the side like this one. And negative 9x squared, that would be 9 of the red ones flipped over. So unlike terms, just as important that we identify these ones. Looks a lot the same, right? Doesn't it? These two look very, very similar. Aren't these like terms? So what's wrong with it? Why is this in my unlike column? It's because it doesn't have an exponent too. They have to have matching variable and exponent. This one's really close because it's got an x squared, but it's also got a y. No good. This one's a denominator. No good. And this one's an x cubed. No good. This is an x squared. So I hope you can see now the difference between like terms and unlike terms. Again, a cornerstone of algebra is understanding what a like term is. So this is our kind of our one and only example today. Simplify. We've got a lot of stuff going on in there. We've got some m's, we've got some n's, and we've got some m squareds. Okay, what are we going to do? Step 1, arrange in alphabetical order, then with the highest exponents first. So I'm going to write this in here. Alphabetical order. That means the m's have to come before the n's, right? Alphabetical order. So I'm going to list all the m's first. But I've got a couple of them. This is an m. I'm going to just use color coding here to help us keep everything apart. I'm underlining all the m's. But these last ones here are actually m squared. They're not the same. So I'm going to, I can only put like terms together. So I'm just going to do one piece at a time. And it says when you have, once we're done with the alphabetical order, so we looked at the m's first, but now we have to look at the highest exponents first. So actually these m squareds are going to be first in our list when we write them down. So let me erase the other ones. So the m squareds are going to go first. So I start with an equal sign, and this is another confusing part. This sign here, subtraction, it actually has to go with the 7. It goes together. You have to take the sign that's in front. So we're going to write that as a negative 7m squared. Negative 7m squared. And then this m squared, the last m squared, I have to take the sign that's in front of it. So that's a positive m squared. You have to take the sign. Have to. have to take the sign that's just to the left of it. You can't ignore it. Okay, we've got the M, so I'm going to switch colors here. Let's go to red. What's next? Well, remember what it says in step 1, alphabetical order, highest exponents first. So we're still on the M's. So here's an M, and here's an M, and here's an M. I underlined 3 different M's there. So those are going to go next in our list. Remember I just made a big deal about taking the sign that's in front just to the left of it? Well, what's in front of this 12m squared? I don't have a sign to take there. If there's no sign, it's a positive. So I have to put that down. That's a positive 12m. And then I'm going to add on 6m. And then I'm going to add on the single m. Now you may not skip the step that we're doing right now. Later, yes. Today, no. You're going to have to show me your work here of you reorganizing everything. You have to do step 1. Okay, we've got all our M's together. Now let's go to the next letter, which is an N. And I'll put kind of a curly bracket under this. We've got a curly line, sorry, a little wavy line here. We've got a negative 5n and a positive 8n. So these ones go together, and way over here we've got a negative n. Those ones I'm going to put all together. They are like terms, and the sign goes with them. So that's a negative 5n, a positive 8n, and a negative n. So we have arranged everything in order, and that was the most complicated step. The next step, step 2, is kind of the easy step. We're going to add or subtract the like terms. So these like terms right here, I'm going to add them together. So I have negative 7m squared. I add on an m squared. What is that going to be? Negative 7m squared plus an m squared. So that's an invisible 1 in front of that m squared. Negative 7m squared plus m squared. Now that we have the like terms, we can kind of ignore them. We can kind of ignore this for a minute here. And it's really negative 7 plus 1. Negative 7 plus 1 is negative 6, and now I've got to put my m squared back on there. So I have negative 6m squared. Next one, I've got all of these m's. I have 12 m's. I add on 6 more m's, and then I add on 1 more m. That's 1m. How many m's do I have? I've got 19 of them. I can't just write a 19m though. I need a sign in front, and that's plus. So I've got negative 6m squared plus 19m so far. And lastly are my n's. I have negative 5n's, and I add on 8n's, and I take away an n. How many n's have I got? So let's do these two first. Negative 5 plus 8, that would be 3, and of course it's a 3n. And now I'm going to subtract an n. That leaves me with a 2n, but of course I have to put the sign plus 2n. And usually we have it written a little bit closer together like this. We would write negative 6m squared plus 19m plus 2n. And I cannot go any further with that. No matter how tempting it is for me to start adding these two, I can't. This is an m squared and this is an m. This is the whole point of this whole exercise here, is understanding the difference between a like term and an unlike term. So I can't go any further. So that is the end of your lesson on collecting like terms. And on your handout, you will see the homework questions that I want you to do. So really important lesson here that you understand your like terms. So I highly recommend when you do a question, you look it up in the back of the book right away, or you look up the answer right away. Did I get this right? Is this right? Because if not, I don't want to keep doing 10 more questions and keep getting them all wrong. So I want to find out right away if I'm getting them right or wrong. So please take a look at the back of the book or at the answers and make sure you're getting them right, and message me if you're getting them wrong.